Hello everyone and welcome back to another maths tutorial. This time we're going to be looking at sequences and limits of sequences. So this is a university topic, maybe a bit confusing at first, but it's very important to understand. So let's just review what a sequence is briefly. So a sequence is a bunch of numbers, usually an infinite amount, following some sort of a pattern is an intuitive way to think about it. So if we start off in the top left, we have 1, a half, a third, and so on. So we can write down a rule for this sequence, which would be the nth term, xn, is equal to, and you can see that it's going to be 1 divided by n. So we get a 1 divided by n. So n equals 1 is the first term, that's just 1. N equals 2 is the second term, that's 1 divided by 2, a half, and so on. And down here, similar thing, 1 plus a half, 1 plus a third, but this time we have to be careful. We've got a 1, we've got an extra 1 added on. So, I mean, it's important to look at what the sequence is actually doing, don't just rely on memory. So 1 plus 1 over, but this time it's not n, it's n plus 1. This time it's n plus 1 because we're starting from a half in our first term, and then we have a third, so n equals 1 here gives us the half on the bottom. So make sure you look at the sequence just to identify the pattern correctly. Now, what is a limit of a sequence? What do we mean by a limit? Well, we really mean an approximation to the sequence, some kind of number that describes the sequence. So let's have a look at our example number 1. What number might describe this sequence? Well, we can see that this sequence is getting smaller and smaller as we go on. So the next term will be a quarter, and then a fifth, and then eventually we get up to 1 divided by a million, and 1 divided by a billion, and 1 divided by a billion billion, and so on. It just keeps getting smaller. So essentially, it's becoming almost zero. It's becoming so small that it's essentially zero. So 0 might be an approximation or a way to describe this sequence. That's an interesting idea. So let's have a look at what the actual definition of a limit is. It says, for every epsilon, this is epsilon, for every epsilon greater than 0, there exists a natural number, m, such that for any n greater than or equal to m, we have absolute value xn minus L is less than epsilon. And we want this condition to hold for some number L called the limit. Now, epsilon is an error term. A natural number, that's just a positive whole number, so like 1, 2, 3, 4, and so on. And this absolute value just means you take the size of the number, or you forget about the sign of the number. So the absolute value of 5 is 5. The absolute value of minus 5 is also 5. You forget about the sign. So think of epsilon as our error term. It's how good the approximation is, how close we can make the approximation to our sequence. So let's go through an example to make this clearer. Let's do number 1. So number 1, well, we said 0 might be a good try because the terms are getting smaller and smaller in the sequence. Let's try 0. So what would we get? We would get absolute value of 1 over n. We will be subtracting 0 for L, so that leaves us with just 1 over n. And we want this to be less than epsilon. Okay, well, 1 over n is always positive, so we can get rid of the absolute value sign, because it means we forget about the sign. We want that to be less than epsilon. And how can we ensure that this is true? Well, we can just rearrange. So let's bring the n up and divide by epsilon, and that gives us that n is greater than 1 divided by epsilon. Okay, so provided this is true, then we will have this condition. So all we need to do, we can just say therefore, these dots mean therefore, we can say therefore m greater than 1 over epsilon will work. I'll put a tick to show that will work. So provided we choose m greater than 1 over epsilon, then we will be fine. Once n goes past this point, this condition will be true. I hope that makes sense. Let's just make it a bit simpler. If we took epsilon to be a half, 0.5, then we'd be saying 1 over 0.5, which is 2. So we'd be looking at m greater than 2. So, for instance, m equals 3 or more would work. And then once n is at least 3 or more, we will be fine. We will have this condition. So that would essentially be saying once n is 3 or more, 1 over n is smaller than a half. So a third is smaller than a half, a quarter is smaller than a half, and so on. So that's all you're doing. You're picking an error term. You start with your error term, then you find a big M, such that past this point in the sequence, you are close enough to L, your approximation. So let's think about example number 2. Let me draw a divide there. So let's think about this intuitively. We have 1 plus 1 over n plus 1. Well, this 1 over n plus 1 is similar to this 1 over n. It's just getting smaller and smaller. So you can say that this bit becomes 0, or gets very close to 0, and this 1 doesn't change, this plus 1. So we could argue that the limit will be 1. And it turns out that it will in fact be 1. Because if you put it into this definition, you'll get 1 plus 1 over n plus 1, subtract 1, which leaves you with the 1 over n plus 1, and then that's essentially the same as this 1 over n, just you have the plus the n plus 1, so you have to incorporate that into your answer. So I want you to try solving this, try proving that the limit is 1, put it into this definition, have a go at it, hopefully it will make sense. If not, go back and watch the 1 over n example again, and just follow the same procedure. So thank you for watching. Next time I will upload some more complicated sequences and how you would find their limits, and I'm going to go into a lot more detail on limits in general of sequences. Okay, enjoy solving the maths problems. Take care.